Hello and good afternoon friends, welcome to CEC live lectures. Dear friends, today in this session we are going to talk on one of the most important topics for the students of chemistry. We know that this topic is very important. Yes, we are going to talk on aldehydes and ketones, and for this discussion we have once again with us in our studios Dr. Aparajita Chauhan. Dr. Aparajita Chauhan is Associate Professor in Department of Chemistry, Sri Aurobindo College, University of Delhi. Dear friends, if you want to ask questions from Dr. Aparajita Chauhan, then you can call us right in the studio. For contacting us, that is for asking questions, you can take help of our toll-free number. Our number is 1-800-110-430. Friends, you are requested to call in the last 10 minutes so that the lecture gets uninterrupted and your queries are also resolved in the last 10 minutes. So you are requested to kindly call from 4:05 to 4:15. So let's welcome our guest Dr. Aparajita Chauhan and let's carry forward the lecture. Hello ma'am, welcome to the lecture.
Thank you, Geetika. Without further ado, I'll start with aldehydes and ketones. So today we are going to talk on compounds which contain carbonyl functional group. So what is a carbonyl functional group? It is a group in which carbon is bonded to oxygen by a double bond. These carbonyl compounds are very important because in them what we find is that the CO group is attached to an alkyl group which we can call as an acyl group. And these carbonyl compounds are of two types, that is on the basis of the reactivity of the group which is attached to them. So what I see here is different classes of carbonyl compounds like ketones, aldehydes, carboxylic acids, acid chlorides, esters and amides. When we talk of ketones, we find that in them a carbonyl group is attached to two alkyl groups, whereas in case of an aldehyde it is attached to one alkyl and one hydrogen. So carbonyl compounds, what we think on the basis of their reactivity, can be divided into two categories. One category is in which the acyl group is attached to a functional group which can be easily substituted. So in case of carboxylic acid, if I see this carboxylic acid is attached to an OH and this OH can be easily replaced by a nucleophile. And then if we talk of carboxylic acid derivatives like acid chlorides, esters or amides. In acid chlorides, the acyl group is attached to a chlorine atom, whereas in case of esters, the acyl group is attached to a alkoxy group, and in case of amides, it is attached to an NH2 group. So what is the difference, or what gives rise to the difference in the properties of the carboxylic groups and the acid halides? Rather, I would say why are they different in reactivity? So what we find is that when an acyl group is attached to a better leaving group, then they are more reactive. For example, acid chlorides are more reactive as compared to carboxylic acids towards nucleophilic substitution reactions. And since they undergo substitution reactions at the acyl carbon, we say they undergo nucleophilic substitution reactions. The other set of carbonyl compounds which are of interest are aldehydes and ketones. In them, the substitution of the alkyl group or substitution of H in case of an aldehyde is difficult because the bond dissociation energy of these bonds is high. So aldehydes and ketones undergo nucleophilic addition reactions at the carbonyl group rather than substitution reactions. So in today's lecture, we shall be discussing aldehydes and ketones in detail. First, we shall be concentrating on the nomenclature of these compounds. Then we will take up isomerism, especially tautomerism, followed by different methods of preparation of aldehydes and ketones. So if I talk of the nomenclature, that is naming of aldehydes and ketones, then we know aldehydes and ketones are the simplest carbonyl compounds. In aldehydes, the carbonyl group is attached to a hydrogen atom, or it may be attached to a hydrocarbon atom like a alkyl, cycloalkyl, or a alkenyl, or a aryl group. So what we find here is that in case of formaldehyde, we are taking H instead of an alkyl group, and formaldehyde is the simplest aldehyde. The next in series, we replace we make this R into a CH3 group, and this molecule is now acetaldehyde. If I look into the next structure, then we have a cyclic structure here, which is a cycloalkyl. And since the CHO is not forming the part of the ring, we name this compound as cyclopentane carbaldehyde. So in these compounds, what we find is that the functional group is CHO, and a alkyl or an aryl group is attached to this carbon, to the carbonyl group. In ketones, the carbonyl group is attached to two hydrocarbon groups. Now these two hydrocarbon groups can be similar or they can be different. If they are different, then we call them as unsymmetrical ketones. And if these two groups were same, that is, if this was alkyl, a methyl group, and this was also a methyl group, then this is a symmetrical ketone. So when we are naming ketones, we can simply name that in a simple manner in a ketone as a ketone. And when I talk of this compound, so I have two alkyl groups here, that is, one is ethyl and the other is methyl. So what we do is we take these groups in alphabetical order and we name this compound as ethyl methyl ketone. Similarly, if I talk of the next compound, it is again a ketonic compound, and we can name this as cyclohexyl methane ketone, methyl ketone. And if we talk of a next ketone, which is an aromatic ketone, again what we find here is that two groups are substituted here on the either side of the carbonyl group, and one is a phenyl group and other is a isopropyl group. So we can name this compound in a simple manner is isopropyl phenyl ketone. So now if we have to talk of the IUPAC system of naming aldehydes and ketones, so how do we name them? Aldehydes are obtained by replacing E of the corresponding hydrocarbon with Al. So now if I talk of the first example here, so we have to follow the same rules that we follow for all other compounds. That is, the longest carbon chain is to be taken as the parent chain with the aldehyde group present in the chain, and we give this aldehyde group number 1. So when we number this chain from here, what we find is that in this molecule we have 8 carbon atoms. So that means it has been derived from octane. So what we do here is we drop the word E of octane, replacing it with Al, and it becomes octadiol. That means octane now indicates that this molecule has 8 carbons in it, and al indicates that the principal functional group in this molecule is an aldehyde group. Now if I look into the other example, this is again an example of an aldehyde. So what we find here is that in this case we have a choice, we have 2 long carbon chains. In one chain we have 5 carbons, 1, 2, 3, 4 and 5. Whereas in the other chain we have 6 carbons in it, and along with the 6 carbons we have a double bond here at the 3rd carbon, and then we have a substituent at this. Now the question arises, which chain is to be taken as the parent chain? So first of all, we are going to take the longest carbon chain, which contains the principal functional group as the parent chain. Then what we find is, in this case there is no ambiguity, because the longest carbon chain has a double bond as well as an alkyl group attached to it. So we are taking this as the parent chain. You could ask me a question, why not this chain as the parent chain? Because when I take this chain as the parent chain, this part of the molecule along with the double bond becomes a substituent, which we don't want. I want to take this as a root name, that is, this compound is a derivative of hexene. So how do we name it now? Starting from numbering at the CHO group. This compound has a double bond at the third carbon, so the root name becomes hexenal. And now we have an isopropyl group at the third carbon. Why is this an isopropyl group? Because this carbon here is ending in 2 methyl groups, so the name becomes 3-isopropyl, and since we have a double bond at the third carbon, 3-hexenal. Now this E here indicates the configuration of the groups at this double bond. That is, the groups having higher priority are on the opposite side of the double bond. This we shall do in detail when we discuss geometrical isomerism. Now in the next slide again, I have continued with the naming of aldehydic compounds, and I have taken here an example of a cyclic compound. Now when we talk of this cyclic compound, what we find here is we have 2 functional groups. One is CHO and other is the bromo group. Now the question arises, which will be the principal functional group? Please remember, according to the priority table, CHO is the principal functional group. And since this CHO cannot form the part of a ring, it is occurring outside the ring, we name this as carbaldehyde. That is, this carbon cannot be included in the carbons of the ring. So this is separately named separately as carbaldehyde, and this carbon to which it is attached is numbered as 1. Then if we start the numbering, bromine occurs at the 4th carbon, which occurs as a prefix before the root name, and the compound is named as 4-bromo cyclohexane 1-carbaldehyde. And this indicates that the 2 groups, the Br and CHO, are on the same side of the plane of the ring, and this we are indicating by using the word cis. Now if we go on to ketones, now the question arises, how do we name ketones? Ketones are named by replacing the word E of the hydrocarbon part with ONE, with one. And when we have to now keep in mind is that we have to do the numbering from that side of the chain, which gives the lowest possible number to the ketonic group. So now if we look into the examples, the first example shows that we have a chain which is having 5 carbon atoms in it, so the root would become pentane. And then when we number the chain, what we find is from either of the side, this carbonyl group is getting number 3. But if we number it from this side going to this, then the methyl group is getting number 4. And if I number it from this side, then the methyl group is getting number 2. So looking into the lower sum rule, what we find is we will do the numbering from the left hand side. So the name becomes 2-methyl, since it has 5 carbon atoms, pentane, and since it has a ketonic group at the 3rd carbon, so it becomes 3-pentanone. Now the next example is that of a cyclic ketone. In this case, the carbon which is attached to the oxygen, or which is the carbonyl group, it is forming the part of the ring. Hence, we will name this compound as cycloheptane, since it has 7 carbons in it, and heptanone because it has a ketonic group in it. Now the question arises, to which group will we give the lowest number? So this carbon here is given number 1. And now we can start numbering from either side because these chlorines are at a symmetrical position. So this becomes 1, 2, 3, 4, 5 and 6. 6 and 7. So what we have is, we have a chlorine atoms at 2nd and the 7th position. So the name of the compound becomes 2,7-dichlorocycloheptanone. So this is how we will name a cyclic compound, giving priority to the ketonic group, if this is the principal functional group present in the molecule. Now let us look into the next compound, which is an example of aromatic ketone. So in this case, what we have is the ketonic group is present in the side chain. So we will name this as, and this chain has 3 carbons in it, 1, 2 and 3. So we will name it as a derivative of propane, and since we have a ketonic group here, this becomes propanone. Now to this carbon, now please remember this carbon is the first carbon. To the first carbon a ketonic group is attached as well as a phenyl group is attached. So how do we name this compound now? This is named as 1-phenyl 1-propanone. This is how we name this compound. Now we go on to a next example again of a ketone, and in this we have different functional groups. Now again, if you observe this compound carefully, we have a ketonic group at the second carbon here, and then we have 2 bromo groups at the second carbon here. But please remember, we will give priority to the principal functional group, so that means we will give lower number to this. So this group will get number 2. And if this group gets number 2, that means this cyclopentyl group here will get number 5. And cyclopentyl group and the 2 bromo groups are now substituents. So they will be added as prefix before the root name. So here the root name is heptanone or 2-heptanone because the carbonyl group is present at the second carbon. So now the name becomes 6,6-dibromo 5-cyclopentyl 2-heptanone. The prefixes are to be added before the root name in alphabetical order. What if we are taking these aldehydes as ketones as substituents? That is what I mean here is that is some other functional group is present which occurs before the aldehyde and the ketonic group in the priority series. So what we do in that case is we name aldehydic group as a formyl in prefix and a ketonic group is named as a oxo again in the prefix. So now if we look into these examples here, so first example is a compound in which we have both the functional groups, that is the CHO group and the ketonic group. Between these 2 groups, the CHO group gets a preference over the ketonic group. So what we'll do is, when we take the longest carbon chain, we will get lowest number to this aldehydic group and it will be named as pentanal since it has 5 carbons in it. But what we observe at the same time, at the third carbon, a keto group is also present here. So we shall name this compound as 3-oxo. Oxo here is a substituent, pentanal. Next compound is an aromatic acid. So we know that carboxylic group gets higher priority over the aldehydic group. That is, this group gets higher priority over the aldehydic group. So here, formaldehyde, this group, the aldehydic group, becomes a substituent and we will take it as a formyl. Whereas if you look into the first example which I had discussed, in this case I was taking it as a principal functional group, so we were naming it here as al. Whereas in this case this will become formyl, and when we do the numbering, please remember the carboxylic group will get number 1. So this group gets number 2 and the name of the compound becomes 2-formyl benzoic acid. Similarly, now if we look into the third example, then what we find here is that this ketonic group is a substituent here. Since it is a substituent, again I am going to use the word oxo for it in the prefix. And then we have a acid, so this will be given number 1, and since this has 4 carbons in it, it will be named as butane. And since it is having carboxylic group, we are dropping the word E of the hydrocarbon butane and replacing it with oic acid. So in all what we find is that this compound has 4 carbons, therefore butane, and it has carboxylic acid, butanoic acid. At the same time, it has a ketonic group at the third carbon, so we name it as 3-oxobutanoic acid. See, this naming is very, very systematic. So if you remember the rules, which groups have to be taken as the priority, and I tell you how to draw the structure of 3-oxobutanoic acid, what will you do? You will simply take 4 carbons in the straight chain. COOH group will come at the first carbon, and then we will put a ketonic group at the third carbon. And the valencies of the rest 2 carbons, we will fulfill them with hydrogen. And hence we can draw the structure of the molecule by just knowing its IUPAC name. Some more compounds by which we will name them by common names. So important carbonyl compounds which can be named by their common names are, first example, which is propanol, which is acetone. Second is acetophenone, again a very important aromatic ketone. And then what we have is a benzophenone. Please remember, C6H5CO becomes a phenone group, right? And then what we have here is a phenyl group, so we are naming it as benzophenone. And we know that aldehydes and ketones form an integral part of our daily lives. Now, if I have to talk of aldehydes, there it is very simple to name these compounds. That is, if we have in a compound just 1 carbon, then we use the word prefix form, and to it we will be adding, for this CHO we shall be adding the word aldehyde. So the name of this compound will become formaldehyde. Now if I look into the next compound, which is having 2 carbons, then for 2 carbons we use the word acid. And since it is having a aldehyde group, the name will become acetaldehyde. And by chance, instead of CHO, we had supposing COOH, then the name would have become acetic acid. Now, if we look into the next compound, it is having 3 carbon atoms, 1, 2, and 3, which are indicated by propion. And then along with this, we have an aldehyde group. So what do? We add the name aldehyde to it, and the name becomes propinaldehyde. Similarly, what we find in case, if a compound has in all 4 carbons, we'll name it as butyl, and the name will become butyraldehyde. If compound has 5 carbons, then it is valeraldehyde. Now, before we proceed further, let us look into this structure here. What we find here is, in all the structures, the carbon which is next to the functional group is known as the alpha carbon. The next is the beta carbon. Then we have the gamma carbon. Then we have this carbon, and then we have the epsilon carbon. So if the substituents are present on these, supposing a substituent is present here, we will say beta beta or beta, whatever the substituent is. We will be discussing the example shortly. Now, if the compound has 6 carbons in it, then we name it as capro, and the name will become caproaldehyde. Similarly, if the molecule has 7 carbons, then the name becomes ethanaldehyde. If it has 8 carbons, then the name is capraldehyde. 9 carbons, pelargon aldehyde, and if we have the 10 carbons, it becomes capraldehyde. Now let us look into this example here. We have to consider here, we are naming it according to, it's a classical example in which we are going to name it as alpha and beta. So what you have to remember here is, again please, that aldehyde group is the parent. So we are naming it as an aldehyde. So how many carbons do we have in this? 1, 2, 3, 4, 5, 6, and 7. And now for 7 carbons, we know that the common name that we can use is enanthaldehyde. So the root name of this molecule is enanthaldehyde. Now in this enanthaldehyde, at the second carbon, we have a methyl group, which is the second carbon. That means this is an alpha carbon. So alpha carbon, we have a methyl group. And when we talk of the gamma carbon, at gamma carbon, we have 2 halogen atoms. So now the name of the compound becomes gamma dichloro 4-methyl ethane aldehyde. And if I talk of the IUPAC name of this compound, then please remember this CHO will be given the priority. So, and it has how many carbons in it? 7 carbons in it. So, the root name will become heptanal. And at the second carbon now we have 2-methyl group. And at the fourth carbon we have 2 halogen groups, that is the chloro groups. So, now when we name this compound, we will name it as 4,4-dichloro 2-methyl heptanal. And please remember again that the substituents are added before the root name in alphabetical order. Now when we talk of aldehydes and ketones, we know aldehydes and ketones are linked to human civilization since the very beginning. So these are very important compounds. Like if I talk of vanillin, vanillin is present in vanilla beans and it is responsible for flavoring. Similarly, the oil of bitter almonds, the smell of oil of bitter almonds is due to the presence of benzaldehyde. Formaldehyde, we know we can use it as a disinfectant. Not only that, there are some naturally occurring aldehydes and ketones which play a very important role in our daily lives. For example, if I talk of glucose, then glucose is a pentahydroxyaldehyde, that is C6H12O6. This molecule is linked with energy metabolism in all living beings, may it be plants or animals. Then another class of compounds which are very important for us is steroids, that is hormones. Now what do we find in common in steroids is that in steroids are polycyclic hydrocarbons, they are fused, and in this what we find here is that if you look into the example, that it has 3 cyclohexane rings fused together. This is the basic structure along with a cyclopentanone ring. This is going to be the basic structure of any steroid molecule. And along with it, now we can have other functional groups present in it. For example, it can have a ketonic group. So this is a testosterone. So what I'm talking, we are at the moment going to talk of steroids or hormones which have a ketonic group. So testosterone is, you know, a very important male hormone which is responsible for the male characteristics. The next important sex hormone is progesterone, which is a female hormone, and it is secreted during the time of ovulation. And what we find here is that this is again having 2 ketonic groups here. One is here and the other is here. Another important example is cortisone. Cortisone is a hormone which is excreted by adrenal glands and it relieves inflammation. And again what we find here is that this molecule has 3 ketonic groups, one here, and the other here. Now a similar compound which is prednisone, it can substitute for cortisone. It is a synthetic drug. If you look into this molecule, this has the same structure as cortisone, and this is used to relieve the symptoms of rheumatoid arthritis. That is, we have a ketonic group here, we have again a ketonic group here and a ketonic group here. Now if I talk of aldosterone, this is a very important, again a steroid, a hormone, which is having a ketonic group here and a ketonic group here, as well as it has an aldehydic group. And this regulates the sodium ion concentration in our body, thus regulating the water retention. So if sodium ions go up, water retention is high. And then we say, what do we say? That sodium imbalance has taken place in the body. So what we find is that these carbonyl compounds play a very important role in our lives. And they are very closely associated with us. So what I think is that we can simply give a lecture only on the sources and uses of these carbonyl compounds, and we can discuss it in a separate lecture later on. Now when we talk of aldehydes and ketones, then aldehydes and ketones, like other compounds, will show all the types of structural isomerisms. That is, they can show a chain isomerism where the chain is branched or straight. They can have a position isomerism, that is ketone show position isomerism, that is in ketone. The carbonyl group can be at the second carbon in case of pentanone 2, or it can be at the third carbon when it is 3-pentanone. Not only this, what we find is that aldehydes and ketones show a very important type of isomerism, which is Keto-Enol Tautomerism. When I talk of Keto-Enol Tautomerism, it plays a very important role in carbonyl chemistry as well as all other organic functional groups. And what is this Keto-Enol Tautomerism? It is a special type of functional isomerism in which there is dynamic equilibrium between the keto and the enol form. So if I look into this series, what we find is this is the keto form here and this is the enol form. So there is a dynamic equilibrium between the two forms. Now when we compare the keto and the enol form, what we find is that if we are talking of a monocarbonyl compound, then in that case the ketonic form is more prevalent. That is, if I talk of acetaldehyde, then acetaldehyde exists as in a ketonic form which is nearly 100%, and the enol is in a very small amount. This we shall take up after some time. We shall discuss a very important type of isomerism, which is Keto-Enol Tautomerism. Keto-Enol Tautomerism is a special type of functional isomerism in which there is dynamic equilibrium between the keto and the enol form. And these two forms are readily interconvertible in presence of acid or base. If we talk of a monocarbonyl compound, then what we find in monocarbonyl compound is that the aldehydic form, that is the ketonic form in case of acetaldehyde, is the major form. That is, nearly whole of the acetaldehyde exists in keto form and the enol form is very small. Similarly, if I talk of acetone, here also 99% of acetone exists in a keto form and cyclohexane exists as 98.8%. That means that this keto form is more stable as compared to enol form. Why is it this so? Because the bond strength of the C double bond O is greater than bond strength of C double bond C. So this molecule will exist more in keto form rather than enol form. Now, if we talk of a dicarbonyl compounds, then what we find in case of dicarbonyl compounds here is, that is, I am talking of a beta dicarbonyl compound here. So what we have here is that this is alpha, this is beta. We have the two ketonic groups. Then in that case, the enol form predominates. Why is this so? Because when we talk of the enol form, if you look here, this is has a conjugated system. So and therefore we can have different resonating structures for it. So the resonance stabilization, because of the presence of the conjugated double bond, makes it more stable. Second part, what we find here is, if you look here, there is the possibility of intramolecular hydrogen bonding here, which makes the molecule more stable. So what we can say is, like if it is a monocarbonyl compound, then the major form will be the keto form, whereas if it is a beta carbonyl compound, then in that case the enol form will be more stable because of resonance stabilization and intramolecular hydrogen bonding. Now, how does this interconversion takes place? It can take place either by an acid or by a base. So if I talk of a base catalyzed mechanism, then what we find here is first a base will remove a hydrogen from alpha carbon. Why does this happen? Because we know that in carbonyl compounds, if I talk of this molecule, then this keto group is an electron withdrawing group. It withdraws electrons towards itself, as a result of which this carbon has a partial positive charge, that is the alpha carbon. And this alpha carbon will pull the electrons towards itself from alpha hydrogen, and this bond becomes weak. Hence, this hydrogen is acidic in nature. So what happens is, when a base approaches this, a base approaches the keto form, it will abstract this hydrogen from here as a proton, resulting in the formation of enolate ion. So what is an enolate ion? We have a double bond here and a negative charge here. This enolate ion is resonance stabilized, as we can see here. That is, it is having a double bond between carbon here and a negative charge here, so it is known as enolate ion. Now what happens in the next step is that the water molecule, that is the solvent, will give a proton to this oxygen, that is protonation occurs, and this keto isomer transfers itself into the enol form. So what happens here first is, base will abstract a hydrogen to form a enolate ion, and then this enolate ion reacts with water to form a enol tautomer. Next, what we can have is an acid catalyzed reaction. Now this acid catalyzed reaction is opposite to what we saw in base. In this case, first what happens is the protonation of oxygen takes place, whereas in base catalyzed, please remember, first a hydrogen is removed from here. So these two steps are just opposite. Protonation of this molecule takes place here, getting into this molecule, this structure, and then the water acting as a base here, that is the lone pair of electrons on oxygen here, act as a base, and they abstract a hydrogen from here, and this bond here, the sigma bond here, goes here to form a double bond, resulting in the formation of ene. And this pi bond here goes back onto the oxygen as the lone pair of electrons here. Why do we call this form as a enol form? That is, a enol form is that in which OH is directly attached to a carbon which is having a double bond. That is, that carbon is attached to another carbon by a double bond. Then one thing which is to be kept in mind is that only those aldehydes and ketones show tautomerism which have alpha hydrogen in them. For example, if they do not have alpha hydrogen, like formaldehyde or benzaldehyde, then if we have to talk of the reaction here, that is, if I have to abstract a hydrogen from here, we do not have an hydrogen which we can abstract from the alpha carbon, and hence they will not show Keto-Enol Tautomerism. So we will be finding that this Keto-Enol Tautomerism will be playing a very important role when we do the synthesis of carbonyl compounds from alkynes. So taking forward from here, let us continue with the synthesis of aldehydes and ketones. We can talk of several methods, but the important among them are hydration of alkynes, that is mercuration, demercuration or hydroboration reactions, then ozonolysis of alkenes and oxidation of alcohols. Then we can even prepare aldehydes and ketones from 1,3-diethane by alkylation reactions. And we know that if we do reduction of acids, acid chlorides and nitriles, we can get aldehydes. then Gilman reaction is a special reaction for preparation of ketones. So let us start with hydration of alkynes. So what is hydration of alkynes? It involves the reaction of a alkyne with H2SO4 in presence of HgSO4 followed by acidic hydrolysis. What happens in this reaction is the overall reaction is the hydration of this triple bond. So what happens is, if we don't go into the mechanism, simply we have to do the reaction. What we say is that OH will attach onto this triple bond according to Markovnikov's rule. That is, OH will go to that carbon which is having less number of hydrogens here, or to that carbon which is more substituted. So it will go to this carbon and H will go to this carbon, resulting in the formation of an enol. Then this enol, in presence of an acid, will tautomerize to give us a ketone. And by chance, if this ketone is, here it is adding according to Markovnikov's rule. Now if this and this, we are having a terminal triple bond here, so we have no other option other than OH going on to this carbon. But whereas if this was an unsymmetrical alkyne, that is, I had this C was attached to another CH3, then in that case the probability of getting two ketones would be there. That is, one would be 3-pentanone and the other would be 2-pentanone. That is, if I take this example as a 2-pentyne. Now let us look into the mechanism of the reaction. In this reaction, please remember that this mercury will act as an electrophile, water will act as a nucleophile. So when this mercury comes to approaches this, here the triple bond of the alkyne is acting as a nucleophile. And now this mercury will attach to a carbon which is more substituted, that is, it will attach here, it will make a bond here through these electrons, and these electrons will form a bond with mercury. These are acting here as a nucleophile and this is acting here as an electrophile here, and resulting in the formation of a cyclic intermediate. Now since this is a cyclic intermediate, that means water cannot approach from this side. Water will approach from the opposite side and it will make a bond with this carbon here. It is acting, water is acting here as a nucleophile. Why is it acting here as a nucleophile? Because this mercury, being electron deficient, will pull these electrons slightly towards itself. Therefore, this will go to this carbon. Now water has added here. In the next step again, and mercury is at this place, the lone pair of electrons on oxygen is forming a bond with this carbon which is electron deficient. As a result of this, this oxygen has a slight positive charge on it. Now this water molecule again acts as a base through lone pair of electrons on it, or it acts as a nucleophile, and it abstracts a proton from here, resulting in the formation of mercuric enol. So let us quickly see what has happened. First, we are getting a cyclic complex with mercury because in this case mercury is acting as an electrophile here. Then in the second step, this water attacks from the opposite side. That means this is an anti-addition. Then the cleavage of this H plus, resulting in the formation of mercuric enol. Now this mercuric enol eliminates a mercury ion from here, resulting in the formation of an enol. So what do we have here? We have an enol. Now in this case, when we have an enol, please remember acid catalyzed tautomerism is taking place here. So when I talk of an acid catalyzed tautomerism, please remember what will happen in acid catalyzed tautomerism is that first a H will come from here. It will go on to this, that is protonation will take place at this position, and then OH minus will act as a nucleophile, or water will act as a nucleophile, and it will abstract a proton from here, resulting in the formation of a ketone. So what happens here is Keto-Enol Tautomerism. So if we now summarize this reaction, what do we say? That water has added across the double bond according to Markovnikov's rule, and the addition is anti-addition. Now the very plus point about this reaction is that in this reaction, carbocations are not formed as intermediates. Now since carbocations are not formed as intermediate in this reaction, no rearrangement will take place. That is, we will get the desired product. Second, the yield of the ketone formed will be high. So we prefer to do hydration, that is by H2SO4 in presence of HgSO4 in conversion of alkynes to carbonyl compounds. And please remember, it is only acetylene which will react with H2SO4 in presence of HgSO4 to give us an aldehyde, that is acetaldehyde. All other alkynes will give us ketones when we do the reaction with H2SO4 in presence of HgSO4 as a catalyst. Now the next reaction that we shall be discussing today is hydroboration oxidation of alkynes. Now what do I mean by saying hydroboration? That is, first in hydroboration step, this involves two steps. Hydroboration, that is, borane will add across the triple bond, and this will be followed by alkaline hydrolysis, resulting in an enol form. And this addition of water across the triple bond is anti-Markovnikov's. So what we find here is that 3 molecules of alkyne react with 1 molecule of BH3 in tetrahydrofurane to yield a borane substituted alkene, which on alkaline hydrolysis then gives us a ketone. Then the enol immediately rearranges to give us a ketone. So in the overall reaction, what happens is that the boron is replaced by a hydroxyl group. So we call this reaction as hydroboration oxidation, because in first step what is happening is boron is adding across the triple bond to give us a boron substituted alkene, which then undergoes oxidation to form an alcohol, that is, boron is replaced by a OH group. So we say it is hydroboration oxidation. And please remember, the overall reaction is addition of water molecule across the triple bond according to anti-Markovnikov rule. And then in this case, what we will get is, if it's a terminal alkyne, we will get a aldehyde. And if it is an internal alkyne, then that results in the formation of ketones. So what happens in this reaction is that in this reaction, BH3 is acting as an electrophile. Why does it act as an electrophile? Because its octet is incomplete. And we know that if we look into the structure of borane, then what we find here is that this borane is using 3 sp2 hybridized orbitals here to form a bond with hydrogen, with the s orbital of hydrogen. Then it has a incomplete p orbital, and this p orbital here, an empty p orbital here, can accept a pair of electrons. Hence, boron is acting as a electrophile. So when this boron comes to the alkyne, it adds to the less substituted carbon of the alkyne, because if we look into the addition of this structure, then what we find is that when boron will add to a terminal carbon here, supposing if I take this example here, so when boron adds here, this carbon here will start developing a positive charge. So if we have a terminal carbon, then boron will add to that carbon which is having less number of hydrogens, because in that case then the carbon which is a secondary carbon will have a positive charge on it. So what we have here is that boron will go or add to the terminal carbon which is less substituted. and the hydride, which is bonded to boron, will act as a nucleophile. In this case, what happens is that the boron and the hydrogen add simultaneously to the triple bond of the alkyne. Hence, we say it is a concerted reaction, and the addition of boron and hydride is from the same side of the triple bond. So, we get a hydroboration here. Now, after doing hydroboration, what we do is we add alkaline NaOH and H2O2 to the mixture when we get a enol form. And this enol form, again, in basic medium, tautomerizes to give us the keto form. So, end product is what? It is the replacement of boron by OH. And the overall reaction is syn anti-Marconic of addition of water. So, what if we look here? Now, what we find here is that this B, boron, goes and adds to this carbon here, and here we will have BH2, and simultaneously one of the hydrogens goes and adds to this carbon. This is what we have here. Instead of borane, we can also take a dialkyl borane, and then this is a boron substituted alkene. And next step, what we have to remember is that we need just one hydride ion to bring about hydroboration. So, we get this intermediate, and then when we do the hydrolysis of this intermediate with H2O2 and NaOH in aqueous medium, this B is replaced by an OH, and this is the enol form. Then this tautomerizes to give us a keto form. So, now how does it tautomerize? What we look here is that when we look into this reaction, this is the enol form. OH will act here as a base, and it will remove a proton from here. When we remove a proton from here, what happens is that this oxygen has a negative charge on it, which goes into the ring to form a double bond here. At the same time, what happens is that this water here is acting here. Water again acts as a acid here, and this donates a proton to this carbon here. So, what happens is that this oxygen, being more electronegative, will pull the electrons towards itself, and this H will come and form a bond here. That is, the pi bond of the double bond here will form a bond here, resulting in formation of a sigma bond in this case. And now these lone pair of electrons goes back into the ring, resulting in the ketone form. So, what do we say? That it is a base catalyzed reaction in which the enol form changes into the keto form. Next, if we look into it, then please remember acetaldehyde, since it is a symmetrical alkyne, then in this case again water will add, and in this case we have no preference. Hydrogen can go here and a BH2 can go here, resulting in the formation of vinyl borane intermediate, which on hydrolysis gives us a enol, which tautomerizes to give us an aldehyde. But what we have to remember is, for converting this boron derivative into enol form, we just need one equivalent of BH3. If two equivalents of BH3 are used, then we will not get an enol form. So, to overcome this difficulty, what we do is we will use a bulky alkyl group attached to boron. Now, let us look up in another example here. Supposing I look into this carbon. Now, the question arises, this molecule of propyne, the question arises, where will this boron go and add? So, it goes to that carbon which is less substituted, because in this case there is going to be less steric hindrance. If it goes here, there will be more steric hindrance. Then the second point what we find here is, when it adds to this, then this carbon will have a positive charge on it, because the boron is acting as a electrophile and the triple bond is acting here as a nucleophile. So, when this has a positive charge on the secondary carbon, this will be stabilized because of the plus I effect of the methyl group, and the H will go to this carbon as a hydride ion. So what we'll have here is trivinyl borane. Now this trivinyl borane, if we add to this borane here another molecule of BH3, then what we get here is a complex which cannot react with H2O2 to give us a enol form. So in that case, what we do is we use di-secondary isoamyl borane instead of using a borane. Now what we find is that this reagent, as you can see here, is a bulky reagent. So since it is a bulky reagent, only one molecule of this will add to the terminal triple bond. So what we have here is the bulky group, and because of this, one of this hydrogen here will go to this carbon and this will come and add here. And now because of the steric hindrance, second molecule of this di-isoamyl borane cannot add to this carbon. Hence, this will undergo alkaline hydrolysis and will convert itself into enolic form. And then this enol will convert itself into, will tautomerize to give us an aldehyde. Now what we find here is, so how do we summarize this? That is, if we add water across a terminal bond of the alkyne, then a ketone is formed, and the addition of the water molecule is Markovnikov's. And if we do hydroboration oxidation of a terminal alkyne, then in that case we get a aldehyde. We are getting a aldehyde here. And when we are doing the hydration with H2SO4 in presence of HgSO4, here the water is adding according to Markovnikov rule, and we get a enol which then tautomerizes to give us a ketone. Whereas when we do the reaction in presence of di-secondary amyl borane, then we get a enol which then tautomerizes to give us a aldehyde. Again, in this reaction there is going to be no rearrangement because no carbocation is being formed, and the yield of the reaction will be high. Now let us look into just two questions. The first question is, what will be the product of if we do mercuric ion catalyzed addition of water, and second hydroboration for 1-butyne. So please remember, when we are talking of 1-butyne and it is a terminal alkyne, we don't have to go into the mechanism of the reaction. What we have to remember is that when we are doing mercuric ion catalyzed reaction, in this case the addition of water across the triple bond is going to be according to Markovnikov's rule, which we will get a enol which will rearrange to give us a ketone. So in this case we will get 2-butanone. Whereas if I talk of hydroboration oxidation, please remember addition of water is going to be anti-Markovnikov's, according to anti-Markovnikov's rule. Then in this case we will get aldehyde, which is butanol. Now if I talk of 2-butyne, then 2-butyne, again mercuric ion will add across it, and what overall reaction is, please remember that the water will add across the triple bond according to Markovnikov's rule, but since this is symmetrical alkyne, we will get again 2-butanone as the major product. And then if we talk of 2-pentyne, this is an unsymmetrical alkyne, so in this case we will get 2-pentanone and 3-pentanone. And if we talk of hydroboration oxidation, in this case we will just get 2-butanone, whereas in this case again we will get 2-pentanone. Next is, there is only one alkyne that forms an aldehyde when it undergoes acid or mercuric ion addition of water. You have to now identify which of is that alkyne which will give only one, which will give us an aldehyde. I think, let's go back to this, that is 2-butyne and 2-pentyne, please remember, will not give, when we do the reaction with hydroboration oxidation, they will give us ketones. So now you have to answer this question yourself and find out which is the only alkyne which will not give us a aldehyde when it undergoes either acid or mercuric ion catalyzed addition of water. Thank you.
With this note, thank you, ma'am. Thank you so very much. Today we had a vivacious session on aldehydes and ketones. And dear friends, if you have any sort of questions which you think has left unanswered, then do write to us at info.cec@nic.in. We will try to give answers to your questions when next time Dr. Aprajita Chauhan visits our studio. So dear friends, keep watching us and keep writing us. Your feedbacks are important for us. We would be meeting again soon. Till then, take care. Goodbye. Thank you, ma'am. Thank you once again.